Yeah, thanks. And I'm very happy to be able to present our work here. So this is actually from my previous postdoc in Spain. And the work is about heavy quasiparticles and cascades in twisted bilayer graphene in the absence of any symmetry breaking mechanism. And my collaborators in this work are Elena Bascanes and Maria Jose Calderon from ICMM-CSIC and Alberto Camiai from University of Buenos Aires. So since we already have a nice introduction about these things, so I will just quickly get through these things. So we have a graphene bilayer, which with a slight relative rotation. So and then we have this large Moiré unit cells. And in the case space, we have small Brillouin zones, and we have 2 copies of it from the 2 valleys of the graphene layers. And at around 1 degree of rotation, we have these flat bands at the 0 energy. And so because of these flat bands, we immediately have a increased effect of interaction in the system. And we see a lot of interesting correlated phases emerging near this magic angle twist. To begin talking about correlated states, the story started from here in 2018 from Pablo's group, where we saw this correlated insulating states at the half filling of the valence and conduction flat bands and this nearby superconducting domes. And so I just want to mention one thing. So this is the actual carrier density, but I'm going to mainly use this one, which is the carrier density divided by the Moiré unit cell area. So per Moiré unit cell, we have 2 electrons and 2 holes where we have this insulating region. And then in 2019, we saw that we can have insulating states at all the integer fillings in the phase diagram, and we have more superconductivity. And then now we know that from various experiments and theory that it's possible that we have many different kinds of symmetry breaking and topological phases in this system. And not just the insulating phase, but we also have a correlated metallic state, where you can see this strange metallic behavior of resistivity for a broad range of doping values, and the linearity goes down up until very small temperature, which is of the order of millikelvin. So as you can see that we already see some signatures in the system, which is very similar to what we have seen in other systems where strong correlation is very important. So the question, the general question that we had in mind is, what is the role of Mott physics? Is it important for this system? And if it is, then what kind of effect it can introduce in the phase diagram? Now, the specific experiments which concerns directly to our results is this cascades of transitions in this system. So here I have this color map, which is from an STM experiment. And this is a derivative of current with respect to voltage, which is proportional to the density of state. So in the y-axis, I have it's the gate voltage that tunes the doping, and in the x-axis, I have the bias voltage. And here you can see this the peaks from the flat bands when the chemical potential is here when the flat bands are filled. Now, something unusual happens when the chemical potential just goes inside this flat band, and you can see that instead of these 2 peaks, which should shift with respect to doping, in this manner, we have this rearrangement of low energy excitations in the form of a cascade. And this one they measured on the AA stacking region of the twisted bilayer. And when they looked into the map for the AB stacking stacked region, they found something like this, where you can see these oscillations in the onset of the remote band. Now, these cascade features have been also found in this inverse compressibility measurement, where they find this sawtooth wave-like profile with respect to doping, and we have these steps in the chemical potential. And one important aspect of this is that this cascade features have been found for a large temperature scale, which is about 50 Kelvin, which is of the order of 10 times larger than the temperature scale where we have the correlated states and the superconductivity. And we also have several twist angles over which these cascade signals are found. So it is believed to be the normal state of twisted bilayer graphene from which the superconductivity and insulating state emerge at low temperatures. So, and this cascades have been mainly interpreted in terms of symmetry breaking mechanism. So now we ask is, what happens if we go beyond the symmetry breaking mechanism of correlations? Can we explain these cascade features from there? And the answer is actually yes. And I'm going to show you how it does. So we already have some idea of how Hubbard model explains correlation, explains some changes in the normal state through this Mott physics. So this is associated to a spectral wave transfer. So in the left, I have this coherent quasiparticle peak. I'm in the non-interacting limit. So this has some bandwidth. And then as I'm cranking up the value of U, you can see that this spectral weight from the quasiparticle peak is transferred to this incoherent Hubbard band. And we have a Mott insulator. And in the intermediate region, we can have something like this, a correlated metal where we have a narrower quasiparticle and along with this incoherent Hubbard peaks. So, so this was the case for a simpler system. And so mainly I'm going to focus on this physics for the case of magic angle twisted bilayer graphene. Then let me briefly talk about the modeling of the system. So there are different approaches that can be taken to model it. But the approach that we take is to have a model with effective Wannier orbitals on this Moiré superlattice. And the reason for that is one, the physics is happening on the Moiré length scale, and the local correlations are better understood if we have an interaction model on the lattice, on a lattice. So what we have is a 8 orbital per valley model. And this model gives us this 8 low energy bands of this widely used continuum model called Witstitzer-McDonald model. And the reason that we need so many bands is not just the 2 flat bands, is associated to something called fragile topology, which I'm not explaining in the interest of time. So because of this fragile topology, we have to have more bands in the model. And this 8 orbital is the minimum number that we need to have a Wannier model that has this all these relevant symmetries for this system. So so here I'm showing the Wannier orbitals on the Moiré superlattice. So you can see this. So there are different orbitals. So there are 3 orbitals which are on this triangular lattice, this formed by the A stacking regions. And there are 2 orbitals in the stacking, AB and BA stacking region, which form this hexagonal lattice. And we also have 3 orbitals in the stacking where it's intermediate. And you can see here how these orbitals are forming these different 8 bands, and which are color coded here. And so, but out of all these, I just want you to focus on these ones, which have which you can see that they have maximum overlap with the flat bands. And so because they characterize the flat bands, so they are going to be the key player in the correlation physics. But I also want to emphasize that these orbitals cannot cover the full flat bands, and there are these leakages, as you can see here near the gamma point. And so that's related to this fragile topology that I mentioned in the previous slide. And so in gamma we have contributions from other orbitals which are less correlated, and where we have the itinerant electrons. So in this way, these localized orbitals are also coupled to these itinerant electrons in these orbitals. So this was the single particle part, and we also calculate the interaction parameter from the Wannier functions. And so there's in the x-axis, I have the distance scaled by the Moiré length scale. So so what we have is basically the density-density interactions. So there are many interactions because we have 8 orbitals. So there are different on-site, inter-site, and interorbital interactions, which you can see, which are color-coded here in these points. But out of all these, the most important one is this one, so which has the maximum value. And this one comes from the on-site interaction between these AAP orbitals. And because these these orbitals are mostly in the flat band, they have a large ratio of this interaction over the bandwidth. So we have 4 of them in total, and so we have 16 strong local interactions, and we have other interactions, and so then we treat these these 16 interactions within dynamical mean field theory. And because the other interactions are also not negligible, but they're not as high as these interactions, so we treat them as within the Hartree approximation, and we have a self-consistency between the two techniques. So with that, I'm going to get into the results. So just to start, let me show you the general effect that the interaction has on the density of state. So on the left, I'm showing you the density of state of the non-interacting system, which has these 2 strong Van Hoff peaks, which has a bandwidth of about 2 to 3 MeV at this angle. And then as I turn on the interactions, you can see that there is a large impact of interaction in the density of state. So on the right, I have the density of state with interaction from DMFT plus Hartree calculation. And you can see that all the spectral weight from this huge Van Hoff peak is now into these Hubbard bands. And this is not just, this not only happens at the integer fillings, but also we have it in the non-integer fillings. Now, let me show you this density of state for a continuous range of doping. So here, so this black and white map is the density of state. In the Y, I have the filling factor, and in the X, I have the energy. And you can immediately see that these broad peaks, which are basically the incoherent Hubbard peaks, how they're forming these cascade-like features. So these peaks start to form at an energy U, which is the Hubbard U of the AP orbitals, and then they moves in this way as I change the doping value, and then they shifts towards the 0 energy. And then they reaches at the 0 energy at the next integer filling, close to the next integer filling, and where we also have this resets where this Hubbard peak reappears. And this happens for all the integers except at the 0 doping, where the peak actually does not reach the 0 energy, but they drift away, avoiding this point in this way. And we have reverse doping dependence, as you can see here. So this one has this maximum weight on the negative energy, and this one has the weight on the positive energy. And as you can also see that there's non-monotonicity in the spectral weight at the 0 energy. So we can see that there are suppression of spectral weight at the integer value. Maybe it's not very clear here, so I'm showing it in this line plot where I have only the 0 energy density of state with respect to doping. And here you can see this non-monotonicity in the suppressions at the integer values, except at this plus and minus 3. Now, this part of this picture comes from this AAP orbitals, which you can see from this orbital resolved density of state. So this AAP orbitals are in this AA stacking region, and they are in the flat bands in the non-interacting picture. And if you now look into the experimental picture, which they have on the from the AA site, you can see that there is a quite good agreement with it. So you can see these cascades in the arrangement of spectral weight, and you can see this drift in the spectral weight here, which is nicely comparable with this one that we have from our calculation. And then the other part of the picture comes from the less correlated orbitals, which are on the ABBA or the intermediate stacking region, which has these oscillations at higher energy. And these oscillations are actually coming from this Van Hoff peaks, which are in this remote band in the NK direction. And so these are now, so there is oscillations. And now if you look at the corresponding experimental figure on which is the DIDV map on the AB site, you can see that there is a beautiful match between the two, the strength in the two cases. Now, we also have the inverse compressibility. So in the left, I have the local chemical potential, where there are small steps with at integer fillings. So this is filling factor again. And on the right, I have the inverse compressibility, which is basically the derivative of this local chemical potential with respect to doping. And here you can see this these strong peaks at all the integers except at plus minus 3. And you can also see that except at the charge neutrality point, these peaks are quite asymmetric, strongly asymmetric actually, and they're asymmetric in an opposite way in the electron and hole dope side. And now, if you also now I want to remind you about this experimental picture where they find this profile of inverse compressibility. You can see this sawtooth-like profile with doping looks very similar to what we have obtained from our calculations. And here, these asymmetric peaks are described as a result of symmetry breaking due to ferromagnetic polarization. But in our case, we don't have any symmetry breaking in the system. And so actually, so in this case, we can actually explain it in terms of the spectral weight reorganization due to correlations again. So if I show you this inverse of density of state at omega equal to 0, you can see this profile, which is almost exactly the same as the inverse compressibility. So now let me, just to understand the cascade a bit better, these cascades a bit better, let me show you the spectral functions. So here I have the spectral functions. And so this is at 0 doping. So the spectral function looks like this. And so you can see that there is a significant drop in the weight near 0, and there are these Hubbard bands. But we still don't have a MOT here because of the contribution from the less correlated orbitals at the gamma point, which comes due to the fragile topology, as I mentioned earlier. And then as we dope the system, the chemical potential shifts. And so we have this asymmetric Hubbard bands here, and but the filling mainly happens in this less correlated orbitals, which you can see because of this filling here, we have this deformation in this itinerant electrons. And now if you, so one thing is that there is a strong momentum dependence of incoherence because of this fragile topology. And then if you look into the fillings of different orbitals, you can see that there's a plateau here because the filling is happening in the less correlated orbitals, and there is an increase here in this figure. Now, so this thing continues until the upper Hubbard band gets pinned to the 0 energy, and we now have only most of the AP orbitals at this 0 energy. So now the filling starts to happen in these orbitals, and you can see that there is an increase in the AP orbitals, the filling of AP orbitals, and there is actually a decrease in the filling of the less correlated orbitals. And so this decrease is mainly because of the fact that the less correlated orbitals are coupled to this AP, strongly correlated AP orbitals. And so there is an energy, and so this is energetically advantageous to have to lose some of the electrons in the less correlated orbitals. And then this thing continues until this filling factor 1, and where we have this, we have a reset. And then, so beyond 1, then we again have the same picture. So the repetition of the same thing where the AP orbitals are becoming incoherent, and we have a filling, and the less correlated orbitals are getting filled until the upper Hubbard band comes to the 0 energy. And this thing continues with doping. And so we have this filling of correlated and less correlated orbitals. periodically because of the coupling between these two types of particles. So now you can see that this non-monotonicity of this profile is similar to these oscillations in the remote bands that we have in this cascade picture. And that's because the energy associated to this band is proportional to the filling of these orbitals. So the upshot is that along with the correlation in the this AAP orbitals, which are the correlated orbitals, the coupling between the two orbitals is also important to have these cascade features. And that brings me to the end of my talk, actually. And so in conclusion, we have studied a DMFT and studied this twisted bilayer graphene within a DMFT and Hartree calculation. And so the main message is that so the spectral reorganization due to local correlations is it leads to this cascades of transitions that we see in the STM experiments and the compressibility, and that happens in the absence of asymmetry breaking. And so along with the correlations in this correlated orbitals, we also have the coupling of the different type of electrons. The itinerant and correlated electrons are also important. And last but not the least, so there is this also establishes a connection of magic angle twisted bilayer graphene with the other system where the electronic correlations are important, like in the heavy fermion system. So with that, I would like to thank you for your attention.